Okay, so we're going to explore that problem 4 on problem set 4, aka problem set 3. And this website from Stanford goes into a little bit more detail than the book does on the derivation. You will see that this website does discuss that Wells turbine a little bit, the one that has the symmetric blades. It spins regardless of the direction that air is flowing. So you can see this is actually a little double arrow here, and here's your wave coming in. Here's your technology, and then as the air goes up and down, the turbine spins. So what we'd like to do is make an estimate as to how much energy is in this wave. So here's the first equation we want to explore, and I'll just follow along and write these down, because it is not simple or straightforward. This is a little bit different from the things we've seen before. So E equals rho g a squared by 2. Rho, so that's the density of water. G, that's the gravitational acceleration. A squared by 2. And if I just sort of draw a wave here, here's the peak, here's the trough. So this is sort of one wavelength, and we can sort of go from neutral to neutral. You could also imagine sort of continuing this up and drawing it peak to peak. So here's peak to...
You can't see that, so.
Oh, is it chopped? Okay, let me, thanks. I don't know why it's getting cropped here. I'll just, I'll draw a line that'll keep me on the page. Thanks. It's happening with my Excel too. It just started happening. Okay, so where are we? So just at the 4. Okay, so that's kind of my boundary. Okay, so if we draw a wave, we can start at neutral, go up, come back through neutral, down through the trough, and back here, and then let's just go back up to the peak. So you could think of a wave as occupying either this space between these two neutral lines or sort of peak to peak. And basically this dotted line is 0, so if the water were completely calm, that's where it would be sitting. So basically the stuff above the water has potential energy. It also has kinetic energy, and the stuff below has, you might call negative energy. But in general, to form this wave, the wind has to blow, etc. And then it's more or less the wind fighting gravity. So now if we've got a little chunk of water here, you have gravity acting on it, so there's your G vector, and then the water itself has some density rho, and then of course we also know our potential. I'm just going to write the two energy equations. So one is E equals M G H. If you remember that from the first bit of 101, so this is going to be E potential, so I'll just put an E sub P, and then E kinetic equals 1/2 mv squared. So the equations, this looks a lot like, well, it looks a little like both. Because you've got the 1/2 there, you've got this A. Where's that coming from? Well, A is the amplitude of the wave. Hey, Rob? So A is the amplitude, and that is the notation that the book uses. And another thing to keep in mind is that on this guy is that A equals H divided by 2. So from crest to trough is H. So it's basically if you were sitting down here in the belly of the wave, and I remember Perfect Storm, like, oh my gosh, here it comes, the wave is going to look twice as tall as the amplitude, right, because you're sitting down at the bottom. So that's the relationship between H and A. So A is the amplitude from neutral, and H is basically double that. So those are, and that'll come in handy here in another second.
What's this one?
Problem 4 on problem set 4, the wave equation, and I didn't quite give enough information to solve it, and the text did not go into quite as much detail. So that's one thing to keep in mind, and that comes from reference 1. And if we go to the bottom of the page, reference 1 is Colossal. And I've got a copy of that here. So this was in 1983, Ocean Engineering, Volume 10, printed in Great Britain. This guy's at UBC. I wonder if he's still there. That's pretty cool campus, actually. I don't know if you ever get a chance in your British Columbia, yeah, definitely check out UBC's campus. It's a sight to behold. So what he starts with, and I'm not going to do all the math. There's a fair amount of calculus in here, but what he's looking at is there's your density, there's your gravity, here's your distance. So that's basic. This is MGH, that little equation, rho, G, Y, and that's a V, the delta V. So whereas rho is mass per unit volume, you multiply that by delta V, and you get mass. So rho times delta V is mass, and then Y is H. So that equation is energy equals MGH. So again, you go right back to our fundamentals. That's the potential energy in the wave. And then it comes down, et cetera, goes through a few things. And here is now he gets into the kinetic energy. And so KE stands for kinetic energy, and then I is it's the internal energy of the system. Best way to think about internal energy is just like a spring, right? So if I take a spring and pull on it, I've taken energy from me. So let's just, and you can sort of treat anything as a spring. This could be a spring that we would bend. So as I bend that spring, the energy goes from me into the spring. It becomes the spring's internal energy. Now I can go somewhere else with it. It releases that, and it does work. And that's where this is coming from. So it's the work term, in the same way that, think of an engine. You spray the gasoline in, you've added to its internal energy, you ignite it, now it does work and pushes the car. So that's how those three energies are set up to work. Goes through a few other derivations, and basically said these three energies have to be constant. It's moving. The water is moving through space. It's got some elastic energy inside, and it's at some gravitational potential. So the higher it is, the more energy it has. The faster it's moving, the more energy it has, and the more you squish it, the more energy it has. You could also take that internal energy, and if the temperature were changing, which it's not, that could also be how much heat is inside of it. Okay, that goes down. Deeper water waves. So again, he's sort of integrating over volume. So basically what he's doing here is taking, we're just kind of looking at this wave as a two-dimensional thing. We're sort of cutting through it. But of course, it has a total volume that's moving. So this triple integral sums up all of that kinetic energy. All right. And so this is what falls out. Ke sub lambda equals lambda by 4 rho g a squared. So I'm going to write that guy down. So I'll just write it as this. Kinetic energy equals lambda by 4 rho g a squared. And then the potential energy, I think that also drops out here somewhere. It's almost the same. It actually is the same, it just writes in a different form. So this is the potential energy is 1/4 rho g a squared lambda. I'll just go ahead and write that down as well. So the potential energy equals 1/4 rho g a squared lambda. And now if we say that total energy equals the kinetic energy plus the potential energy, that equals just these two guys together, so lambda by 4 rho g a squared. And if you stare at this long enough, you'll see, gosh, they're the same. Plus 1/4, and I'll just keep it in its original form. Of course, you're sort of seeing the stunning conclusion here, but that just comes out to be energy equals lambda by 2 rho g a squared. So if we do the let's just do the dimensional analysis on this really quick. We've got length, we've got mass, we've got length squared, and in the bottom here we have from density we get length cubed, and then we have time squared, and we end up with so that's length of fourth. It's equal to mass. Let's see, the fourth to the third, we're left with 1 over time squared. So obviously, energy MLT squared, sorry that got a little bit small, but those are not the conventional dimensions for energy, so it's basically energy per length. It's energy per, in the SI units, then it's energy per meter, but we're sort of in wave land here, so it's energy per wave, however long the wave is. That's what that means. And that's why when we look at this paper, you can sort of see, it's potential energy per lambda, per wavelength. So that's why the units are a little funky. Okay. For this problem, though, we want to get to power. So right now we've just got this weird energy form. And the way to do that is like so. So typically when we think of power, if we just sort of do a quick review, we know in general power equals force times velocity for a linear mechanical system. We also know that power equals tau times omega for a rotational mechanical system. We also know that power equals I V for a electrical system. But in this case, what we're going to look at is power per unit length equals this energy times volume, or times velocity, sorry. So let's make sure this guy is let's put a little deal there for voltage. So this again is velocity, the same velocity here. In this case, we're looking mainly at solids. These are sort of solid systems. But in this case, we've got a wave system. Okay, and then here's where we can finally solve this problem, because in the case of the wave, we know that the velocity of the wave equals gravity divided by 2 omega. So what this says is the more gravity I have, and the more gravity I have, the faster the wave is going to go, and omega is just the frequency of the wave. So it's not unlike a pendulum system. So if you didn't have any gravity, the pendulum would swing. If gravity is greater, then it swings faster. So think of it that way. And so from there,
So then is W is equal to lambda then?
no, lambda is the wavelength, and omega is.
Those are frequencies, but-
Yeah, right, exactly. Yeah, and then the other thing to keep in mind, there's a few other things. So the T equals 2 pi by omega. So remember, omega is in hertz, and T is in seconds. So in those charts in the textbook, it says it's the time between the waves. T, if it's one wave every 8 seconds, T would be T would just be 8. If T were, let's just say, if T were approximately 6, say T were approximately 6 seconds, we can rewrite this as omega equals 2 pi divided by T. It's not running off the page yet, is it? Okay, good. Is approximately 6 divided by 6. It's approximately 1 radian per second, and it's not one radian per second, which is a little strange. But if you were to be out in the ocean, and let's say you've got your buoy system here, and it's heading up and down. If T were 6 seconds, it would take it 6 seconds to sort of get from neutral up and then back down, and that would just basically be one cycle. So that's what omega is measured in. Okay, so from there, so V, so let's get our equation for energy. Energy, which was this guy right here, rho G A squared by 2. So again, energy equals rho G A squared by 2. V equals G omega, so power equals rho G A squared by 2 times G 2 omega equals rho G squared A squared by 4 omega. Yeah, and then omega equals 2 pi by T. We've already got that. And I already told you that A equals H by 2. So if we take omega and A, so that guy goes in there. Oops, no, the other way. This guy goes here into A. This guy goes there into omega. I'll start on a fresh page. We come up with our final solution, which is that power per unit length equals rho g squared t h squared over 32 pi. So so that we were looking at 4 before. If you square A, this 2 in the denominator becomes 4, and then the additional, the 2 pi comes from this term. So we've got basically 3 additional 2's. 2 times 2 times 2 is 8. 8 times 4 is 32, and that's where the 32 pi comes from. Here we go. So let's just do one quick example. Some of the numbers that are coming out of these papers. Let's look at the other paper. So the other paper that was quoted was Thorpe, report produced for the UK Department of Trade and Industry. And this came out about 15 years ago. So, England, there it was, superpower for a number of years. And we read all through, Watt and Joule and Newton. And I think, Great Britain has a lot to thank to these industrialists who, figured out the steam engine, figured out, combustion motors, et cetera, basically allowed them to drive wherever they wanted all over the planet, set up colonies and things like that. But then, we dug up all our coal. We can't power our steam engines with coal anymore. And then we fracked a lot of that gas off the North Shore. Where's our energy going to come from now? Well, hey, how much energy is in that ocean, boys? Go out and and girls go out and solve that. And that's what you can see. There's a lot of energy out there. There's a lot, and it's kind of more than you would think. It's a lot more than you might think at first hand. How much energy is sitting out there it's a little too big, isn't it? In the ocean. Okay. So concentrates on devices for which new data have been produced since the earlier review. So they're also looking at what technologies are coming online to make wave energy cheaper, more affordable, more sustainable, et cetera. First commercial. This is oscillating water columns that we were looking at before that were on that Stanford site. Okay. So let's just take a peek at this. So shoreline, near shore, and offshore, and the textbook does a pretty good job of showing those three. We saw the figure with what's way out there, what's close, and what's onshore. So 50 terawatt hours offshore. 120 gigawatts too. That's not bad either. 120 gigawatts. That's 60 coal strips sitting out there. 60 coal strips sitting right out there in the ocean, ready to be tapped. And I think the Osprey might even be there. Might even be a picture of that in the textbook. Okay. Here's another thing that's critical, and if you go into this industry, you'll see this exact analysis time and time again. What's the cost? And at what point does electricity become expensive enough that it's time to go and deploy a new device? So they're looking at pence per kilowatt hour, which is very similar to pennies or cents per kilowatt hour. Montana's somewhere Somewhere down here, you can see earlier, they were more expensive. Now as the technology advances, just like we've seen in solar and wind, the price per kilowatt hour comes down. Cost of electricity, again, it's coming down. These are specific. There's the Edinburgh duck bobbing back and forth. They're looking at export potential. I mean, there are some pretty big cables, mega grids that do push these electrons back and forth. And there's a couple little, there's the duck, the frog. Just want to do one little calculation. So it's kind of looking for energy. And here's a shot at how you set the thing up. Take a look at it. Where's the power? And this is basically what we're doing right here. This is the step where we are. The directionality factor, we saw that in the book too. Where's it coming from? Can you capture it? And then sending it out. So this is the same in any type of big energy system. And here's some of the same equations. So that we were just looking at how the wavelength is proportional to gravity, the frequency, and here's the power equation too. So whoever was teaching that physics course at Stanford, Physics 240, went out, grabbed this report, said, hey, here's what I'm going to go with. So let's go back. So there's kind of the final answer. And I just want to do one little equation. What's that?
Let's plug some numbers.
Yeah, let's plug some numbers in. We did this a while ago for like just the Clark Fork. If you built the shallow dam, and there's 1 to 2 megawatts of juice flowing through that bad boy right there. Okay, so again, we're looking at shorelines. Let's just take a bird's eye view. And let's just say we're going to build a device that's as long as that bus out there, 10 meters long, 30 feet long. So we'll just hold that thought. So we're going to have the length equal 10 meters. Now for density, we're going to do everything in SI units, so we'll keep it simple. So rho equals 1,000 kilograms per cubic meter. We'll let gravity equal 10 meters per second squared. Now for this guy, I'm trying to think of like a windy day, maybe at Flathead Lake, and let's just say there's a wave coming in every 10 seconds, just not 1 second, not 100 seconds. Let's just say 10 seconds. Let t equal 10 seconds. 10 seconds, and let's let h top to bottom. But I've seen waves that big at Flathead. Let's just say 1 meter. 1 meter. 1 meter. Okay. So from here, let's see if I can sneak this in. Actually, I'm going to erase my little diagram. It wasn't doing us much good. I'll put it up top. Ten meter system. Okay, so the power per unit length, and I will keep the units just so we can get everything straight here. So the power per unit length equals 1,000 kilograms per cubic meter times 10 meters per second squared, and remember we have to square this. T is equal to 10 seconds, and H is equal to 1 meter squared. And then down here we have 32 pi. Let's just see if we can get a slick number for that. 32 times pi equals, I like 100. 100 sounds good to me. Okay, so here's 100. All right, so 1,000 times, now, so this is 1,000 times 100, right, because it's 10 squared. So that's 10 cubed, 10 to the 4th, 10 to the 5th, 10 to the 6th, if I did that right. 3rd, 4th, 5th, 6th. That's 10 to the 6th divided by 10 squared. And now let's check out our dimensions. So I still have kilograms survive. I've got meters. Got meters squared. I've got meters to the 4th power, and I've got per meter. So per meter comes out. And then I've got, what do I have? I've got seconds to the minus 4th times second to the 1st. That's seconds cubed. Oh, and I screwed up my meter. Meters belong in the, sorry, meters belong in the numerator. So it's kilogram meters per second it's cubed. So if you remember, watts are measured in kilogram meters squared per seconds cubed. So again, this came out nicely because it's watts per meter, watts per unit length. So what we came up with was watts per meter. Well, what is that? It's 10 to the 4th. It's 10,000. 10,000. Right? Watts per meter. So we've got 10 kilowatts per meter. And if our device is 10 meters long, we're talking 10 meters long, we're talking a 100 kilowatt device. That's a lot. That's a lot. Yeah, that's a city block. And who'd have thunk it? So the question is, hey, can you go out and build this thing for $100,000? If you can, then it's $1 a watt. Pretty cheap. Okay. Yeah. Well, there it is. And of course there'll be efficiency issues. And then you get back to the argument, well, the wind doesn't blow all the time, the waves aren't slapping all the time, but hey, something's better than nothing. Go.
This problem set as tricky?
No.
I'm not already going on this, but I got three questions.
It was so straightforward, I got it done really fast, and then I was like, I don't think I know how to do
Okay,
this.
good.
I think I just got a little creative with this one, was all. Yeah. Okay, well, that's pretty much it. I've seen summary 4s are coming in. So summary 5 is left. We'll start, it's Thursday, so we'll start on geothermal. We'll do geothermal next week. We'll do integration the following week. I will put a final out there if you want to take it. It's just kind of for fun. It's bonus. I think everybody's been doing well enough on their exams. It's not going to be necessary, but if you just want some more torture,
Will
I'll
we be able to see
post
your
it.
exam grades at some point before we decide whether or not we want to?
Oh, are they not coming through in Moodle?
No, they're not on Moodle.
Really?
None of
Okay.
them are.
I'll make a note of that. Sorry about that.
And then I just noticed right now.
Because I can see them. They're all really, really good.
Oh, okay. That's good to know.
Yeah.
I just noticed that there's another problem set that's on Moodle that's not listed in the syllabus.
Yeah.
Yeah.
I've really backed off. I used to
Okay.
have 5 problem sets, and it was just too much, so just the 3.
Okay.
Just the
cool.
3.
I'll just ignore that.
Yeah, just ignore the 5th one.
Just have one more summary, and then the exam.
Yep. All right, well, Kathleen Todd is, asking we head over to the Oval, so I figured I'd fire over there. They're just kind of doing their Sustainaganza. I'm gonna plug my book a little bit. Here it is. My daughter did the cover art. That's finally.
Did Rob get that?
Oh, yeah, here's the cover for the book, and it's, should be out in a month or so, but I've been living landfill-free for 6 years, and just saw Martin No Runner. He's got really the only glass recycling, well, there's Bayern that'll take their glass back, but Martin does some pulverizing and does some neat stuff for landscaping and countertops and building facades. There's a Missoula Federal Credit Union's got glass in their facade. And anyway, in the book, I talk about a lot of other, creative ways to sort matter. So we'll plug that a little bit and, see where we go. Okay, guys, thanks, and we'll see you Tuesday. And I'll make sure those grades are visible for the exams. It's always something. Okay.